Hello and good evening. My name's Brian Lawson. I'm the Technical Director for Projex Solutions Ltd, who are a project management and engineering services company based in West Yorkshire, and we've also got an office up in Teesside in the northeast. We're hosting this series of lectures in support of the West Yorkshire Area IMechE committee, and this is I think it's the fourth, if my memory serves me correctly. I'm sure Dan will correct me if I'm wrong. Fourth in the series, and the subject is heat exchange. This series of lectures have been run previously, but we're running this series in collaboration with the University of Huddersfield. So thanks to Josh and Carl from the engineering department. The lectures are aired over Teams and presented by Dan Wells, who is the National Consultant Specialist for Spirax Sarco Ltd. In a moment, I'll hand over to Dan. Just some basic logistics. The presentation will last approximately 50 minutes with the opportunity for Q&A at the end. If you please use the chat function, you should see a button at the top of your screen saying Q&A. If you use the chat function, I will do my utmost to monitor them through the presentation and see if we can push any out while Dan's presenting, and any that are left, or if it's appropriate, we'll keep them all to the end and cover them off at that point. So without further ado, there's maybe one or two people still to connect in, but I'm sure while Dan's introducing himself, that'll happen. So over to you, Dan.
Great, thanks for that introduction, Brian. And also just to mirror the thanks to Projex Solutions, the IMechE, and of course also the University of Huddersfield, without which this series of presentations wouldn't be possible. And I think the key word there really is series. The presentations that we've put together are intended to run as a series, which essentially means that over the past few weeks and over the coming weeks, we will be going through a number of different topics surrounding steam. So it's really intended to be a journey. And I've introduced Spirax Sarco as a group of companies on a number of previous occasions in the previous webinars. So tonight I'm speaking to you on behalf of Spirax Sarco's Steam Thermal Solutions team, which comprises of a number of different companies that you can see under that banner. But what I also want to emphasize is that whenever we think about steam, traditionally we may have thought of it as being a relatively dirty source of energy, because traditionally we've had to burn a significant amount of fossil fuels in order to generate that high pressure, high temperature media. And that simply isn't the case. There are a number of different technologies that sit under Spirax Sarco's Electric Thermal Solutions division that can essentially decarbonize steam. We can use grid or renewable electricity to generate green or sustainable steam, which in turn means that our client can achieve that net zero without any significant modification to their infrastructure. There's been a couple of recent investments by Spirax Sarco into emerging technologies such as molten salt battery storage under Kyoto, and also high pressure, high temperature heat pumps under SPH, Sustainable Process Heat. And of course, I've also introduced Spirax Sarco in the UK and Ireland. Please do remember that very, very useful series of resources that we've got available in the form of guidance documents, tutorials, white papers, calculators and configurators. Remembering that those calculators and configurators are not only very, very good for the basis of design, but they're also very, very useful to help us calculate our clients' cost of steam. So please do check those out. As I've mentioned, this is a series of 60-minute CIBSE approved certified CPD presentations. So if any of you would like to receive a PDF of the slide deck that we're going through this evening, or a PDF of an attendance certificate, please do reach out to me directly. and I'll make that happen. And also, if you've got any questions as we go through the presentation, as Brian quite rightly said, please do drop them into the chat function. So week one, we looked at the basic properties of steam, the fundamentals, the relationships that steam has that other sources of energy, like water, for example, simply doesn't have. The most important takeaway from that first presentation was the importance of keeping the steam as dry as we possibly can. By keeping the steam dry, we're maximizing the energy content and we're minimizing the risk that it can cause damage to the infrastructure. Week two, we looked at the best practice in how we move the steam from the point of generation in the boiler house, what can often be thousands of meters around site, to the various processes and heat exchangers. Last week, we looked at what I believe to be the single most important component of the steam distribution network, the steam trap. In other words, how we can separate the steam as a gas with that high energy density to the condensate as a liquid, hot water. It's unwanted if it were left to remain in the infrastructure and within the heat exchanger, but it does have a value if we can get it back to the boiler house. So steam trapping is fundamentally important if we want to have a steam system that is working with a low burden of maintenance, safely and efficiently. So today we're going to move forward and we're going to cover off what is perhaps the single reason that our client actually has steam on their site or in their process. In the first case, we're going to look at heat exchange or heat exchangers. So when we think about heat exchange or heat exchangers, it's a very, very broad and wide terminology. Any item of capital equipment that takes the heat from one source of energy, for example, steam, and puts it into something else. It could be air, it could be domestic hot water, it could be milk or orange juice. It doesn't matter. The energy is transferred across the thermal barrier without the steam actually coming into contact with the process. So a heat exchanger, it could be a calorifier or a shell and tube heat exchanger, for example. It could be a coil running through an air handling unit. It could be a plate heat exchanger. It could be a jacketed vessel. It could be a bioreactor. They're all variants of heat exchangers. As far as today's presentation is concerned, I'm probably going to use the reference point of plate heat exchangers for the simple reason that they're very, very commonly used and employed across a very, very broad range of industries. Food, beverage, pharmaceutical, universities, hospitals, for example, they're very, very commonly used. So in today's presentation, as I mentioned, please do bear in mind that this is intended as a series. So we're going to build on some of the concepts that we've learned in the previous presentations. We're going to cover off why steam is such an attractive source of energy for heat exchange. We're going to look at different heat exchanger types. We're going to look at the control philosophy. And we're also going to look at some of the consequences of not having the appropriate condition of steam. And also we're going to look at some of the things that can affect steam heat exchangers specifically that may not necessarily be concerns if we were using water as a primary source of energy and as an alternative to steam. So it's that dreaded slide again, I'm afraid. It's the slide that I've shown on previous occasions. And the good news is I'm not going to dwell on this slide too much because hopefully the takeaway from those previous presentations is, well, the steam tables, they're a fantastic tool for steam engineers. They help us make sense of all of those complex relationships between the pressure and the temperature, the pressure and the volume, and the energy content, whether that be water as it's brought to the boil, the energy we need to add to the boiling water to make it change state, and also the total heat energy of the steam. But hopefully, having attended the previous presentations in the series, hopefully you're well aware of the caution that I apply to this slide, and that's that we can only rely on the steam tables with 100% reliability and accuracy when the steam is 100% dry. You remember that if the steam's not sitting on that dry saturated steam line, we are going to have wet steam. And wet steam essentially means that we're likely to get more mechanical damage to the infrastructure. We're likely to see more erosion, corrosion, water hammer. We're likely to have more heat loss because wet steam gives up its heat energy far more readily than dry steam. So there'll be more steam lost as it condenses out in that 1,000 meters of infrastructure. And of course, if the steam does get to the heat exchanger in a wetter condition, it's going to have far less heat energy contained within it. So keeping the steam dry is vitally important, especially when we're talking about steam at the process. The wetter the steam, the less energy, and the wetter the steam, it's likely we're going to have a reduced mass available as a result of that steam condensing out in the process. So we've mentioned that we move steam in accordance with the pressure drop around the infrastructure. In other words, if we're generating steam in a boiler at 10 bar gauge, the benefit is at that high pressure, the steam's got a very small volume, and therefore we can move it very quickly, thousands of meters around site without the need to pump it, and we can do so in a very small infrastructure. So of course, we need to depressurize the steam at the heat exchanger. By depressurizing the steam at the heat exchanger, the steam can move. But of course, as the steam depressurizes, it's going to want to expand. Now that's going to give us a significant benefit because when we depressurize steam and it expands, it means it's going to move across the entirety of that heat transfer surface area very quickly and very efficiently. Now, the little image that I'm trying to show up in the top corner of that screen is what happens if we put a kilogram of steam into a sauna, for example. Now, that steam is going to expand significantly and spread out and occupy every corner. But if we used hot water as an alternative, we just end up with a puddle on the floor. So we're not using that heat transfer space very efficiently at all. So that means, well, that's one of the reasons why steam heat exchangers are far smaller in footprint than water-to-water heat exchangers. It's because we can use the heat transfer space that is available very quickly and very efficiently. Another benefit of using a steam heat exchanger is we've got that pressure-temperature relationship that we spoke about that doesn't exist with water. So if we need a particular temperature at a process, we could need a temperature of, 130 degrees. It tells us that if we need a temperature of 130 degrees, all we need to do is manipulate the pressure to 2 bar gauge. We don't have that pressure temperature relationship with water. So it tells us it's very easy to control the temperature of a steam process by nothing more than a very simple 2-port spring acting pressure reducing valve. We could also use a control valve that's shown on the screen for those more sophisticated processes, but importantly, it only needs to have 2 ports. And also it tells us that we need a good number of pressure gauges on that heat exchanger and around the process, because if we don't, we really don't have much of an understanding with regards to the temperature that steam carries. So just a quick little graphic just to pull some of the benefits together that we've gone through in previous weeks. First thing we want to do with the steam heat exchanger is vent the air away, remembering that steam is a huge barrier to heat exchange. And because steam's got such a high energy density, and because we can use the heat transfer surface area so efficiently, it means that we can warm the process up far more rapidly and far more readily than if we were using water as an alternative. Of course, we can control the temperature very easily just by manipulating the pressure, and we don't need a sophisticated series of pumps or other controls in order to maintain the appropriate temperature of the process. So there are a number of benefits in using steam, but we need to apply the appropriate best practice in moving the steam, keeping the steam at the best condition, and also controlling the steam at the process in order to achieve that. So there are a number of different thermodynamic equations that apply to steam systems. I'm going to go through the three most basic thermodynamic equations to help us understand heat exchange. So the first equation that I'm going to start off with is equation number 1. That applies to the very, very far right of the screen. So let's think about a heating circuit. Let's think about using steam to heat up a circuit of pumped water. So we could be heating the water from maybe 70 degrees up to 90 degrees, for example. And the equation that you can see at the bottom of the page, that's going to help us to determine how we can start to look at sizing the heat exchanger itself. So if we're pumping water, then the information that we need to know is as follows. First of all, it's the mass flow rate of water that is being pumped, either in kilograms or in litres. It doesn't really matter. We then need to look at the specific heat capacity of whatever it is that we're heating up. Well, as I've mentioned, on this occasion, it's water. Other applications, we may be heating up orange juice, or we may be heating up oils or dairy produce. Every process is going to have its own specific heat capacity. In the case of water, that specific heat capacity is going to have a value of 4.19 kilojoules per kilogram for every degree we're elevating its temperature by. So if we were pumping, for example, 2,000 litres per second, we would then need to multiply that by 4.19 and then multiply that by the temperature lift, which we mentioned could be 70 up to 90. In other words, we'd multiply that by the 20 degree delta T. That helps us calculate what we call the Q value, or the heat transfer rate. It tells us how much energy that process needs to take on. That's the first equation. The second equation, that helps us to determine the size of the heat exchanger itself. And again, we want to calculate that Q value, the heat transfer rate. So you can see the equation at the bottom of the screen. U multiplied by A multiplied by T1 minus T2. So the U value, that's the speed at which the heat energy can move across the thermal barrier. We can also call it the heat transfer coefficient. Now, that information should be badged on the manufacturer's heat exchanger. If not, it should be available on the manufacturer's thermal energy data sheet. If not, we can go back to first principles and we could calculate what we expect it to be if we know the surface area thickness and the material construction and the risk that it could be fouling, for example, the U value. We then want to multiply that by the heat transfer surface area. And again, in an ideal world, that's going to be easily badged. If not, we want to access that information on the thermal energy data sheet. And again, if that isn't available, we can go back to first principles and calculate what it is. And we then want to multiply that by the temperature difference. Now that's the temperature difference of the steam on the primary side and the average temperature of the water on the secondary side. So if we take, if we're lifting from 70 to 90, the midpoint is 80 degrees. And if we know the pressure of the steam, then we're able to determine its temperature. So we multiply the U value by the A value, by the temperature average of the primary side and the secondary side, and that is going to help us calculate that heat transfer rate. It's helping us calculate the size of the heat exchanger that's required to provide the energy requirement of the process. And the third equation, that's really looking at how much steam we need in order to ensure that we can get the energy not only into the heat exchanger, but across the thermal barrier to heat the process up at the appropriate rate. How much steam do we need? So we want to calculate the Q value. And again, the Q value tells us that we can understand what that is by multiplying the mass flow rate of the steam in kilograms per second. And we multiply that by the energy content of the steam, that latent heat energy, the useful heat energy I keep talking about, that we can achieve from the steam tables if we know the pressure of the steam. That's going to help us to calculate the Q value. Now, of those thermodynamic equations, of all three, you'll notice that I keep mentioning the Q value. The Q value remains the same. So if we've calculated the Q value in one part of the equation, we can transpose that at a different part of the equation. For example, if we've calculated the Q value from equation 1, we can take that and we can use that information to help us understand how much steam's required, and vice versa. If we know how much steam's available, then we know the extent at which we're able to heat another process up, for example. So the other thing is, it's basic algebra. If we've calculated, if we know what the Q value is, but there are unknowns at different parts of the process, we can change the equation round to use the known values to calculate the unknowns. For example, if we know the Q value, but we don't know the steam pressure that we need, then we can transpose that equation to determine the pressure that is required in order to achieve the appropriate heating of the process. Like I said, there are a number of different thermodynamic equations that apply to steam systems. These are the three most basic. And in order to use those, in order for those equations to apply, we generally make the assumption that there's going to be very, very little, if any, heat loss across the heat exchanger itself. Now, of those equations, you'll notice I mentioned the U value, or the heat transfer coefficient. That's the speed at which we're able to get the energy from the steam and into the process. It's the rate at which we can use that valuable energy in the steam. And because steam gives up its heat energy by condensing and not by cooling down like water does, it means the movement of energy is about 3 times more rapid. Again, that's yet another reason why we need much smaller heat exchangers on a steam system than on a water system. You know, for one, we're using that heat transfer surface area very, very efficiently. For two, we've got a very, very high energy density with steam. And for three, we can use that energy more rapidly. So that U value, it tells us that if we look at that thermodynamic equation up in the top of the screen, it tells us that if we've got a very, very high U value, we don't need quite as high a heat transfer surface area. So the A value can be much smaller. And it means that we can really play tunes with those values. For example, if we've got a high U value, but we've also got a very, very high A value, it tells us that we don't necessarily need quite as much steam as we thought we may require in order to elevate the temperature of the process. We can play tunes with those values very, very quickly and easily. Okay, so it's back to those steam tables again. I mentioned the importance of doing everything we can to distribute the steam at the highest possible pressure. High pressure means we've got high temperature steam, but what you'll notice in that middle column, the enthalpy of evaporation, which we also call the latent heat or even the useful heat, high pressure steam's got far less energy contained within it than low pressure steam. So we know the benefits of reducing the pressure of the steam right next to the heat exchanger. We can control the temperature. We can allow the steam to depressurize and spread across the entirety of the heat transfer surface area very, very quickly. And we can also control the temperature. But you'll notice that if we can condense the steam at a very, very low pressure within the heat exchanger, you can see this far more useful energy available. In other words, we've got a benefit in terms of efficiency. So if there's more energy present within the steam, and if we've got a very, very high U value, it means we don't need quite as large an A value. We don't need quite as large a heat exchanger. So again, that's helping to explain another reason why a steam heat exchanger has got a much, much smaller footprint of space compared to a water-to-water heat exchanger. So if we've got a smaller solution, a smaller heat exchanger, we're not going to have as much heat loss being radiated out from that lump of metal. So we've got a greater efficiency. And of course, a smaller footprint of space is also going to be advantageous because we can get more heat exchangers within a footprint. So smaller buildings, smaller plant rooms, and smaller processes. It's all going to have an advantage. Okay, so I've spoke about the steam tables being such a fantastic tool for us. I've spoken about those calculators and configurators that can help us size heat exchangers. And I've gone back to first principles and thought and spoke about those thermodynamic equations as well. What we can see on the screen, your university lecturers will probably shoot me for, but what we generally do if we're wandering around a client site and we need a very, very quick understanding of the capabilities of a steam system or the requirements of a process, the rule of thumb tells us that if we need a kilowatt of heat, then it tells us that approximately 1.8 kilograms of steam per hour will help us achieve that, and vice versa. As I say, this is very, very much a sanity check, a rule of thumb. It doesn't take the place of those steam tables, the configurators, all those equations. It just helps us to evaluate whether or not a process is likely to be viable at a very, very high and initial stage. So heat exchangers. As I've mentioned, there are different types of heat exchangers. It's a very, very common and broad terminology. The steam does not come into contact with the product that we're heating. So that means that once the steam's done its job, once it's heated the product up, once it's given up its energy, once it's changed state to condensate, we need to get that condensate away very, very quickly, because if we don't, we're in danger that the condensate is going to back up and flood the heat exchanger. And we spoke about that in some considerable detail last week. So on the screen at the moment, you can see that over towards the left-hand side of the screen, we've got one of those, it's a shell and tube flow type heat exchanger. It's got a buffer vessel of hot water that surrounds the tube heat exchanger, and generally this was very, very popular, and it still is reasonably popular in a number of different heavier industries. Commonly, it would be very popular in a broader range of industries up until relatively recently. So what we've got is we've got a tube bundle. We've got a bundle of steam passing through a buffer vessel of hot water. So we're going to be moving the steam across a relatively small heat transfer surface area. That bundle of tubes got a relatively small heat transfer surface area, so we'd express that as having a very, very low A value. And those tube bundles are susceptible to fouling and scaling. So that might have a slightly lower U value than we may otherwise like. And that in turn means that we need the steam to exist at a higher temperature, at a higher pressure. And as we know, that means that it's going to have slightly less useful heat energy contained within it. It's also quite a large footprint of space because we've got that vessel, that buffer of hot water. So it takes quite a long time to elevate the temperature of the process, and we're going to have a reasonably erratic temperature profile of that water in storage. Now, the alternative is that plate heat exchanger that I've spoken about that we can see on the opposite side of the screen. Now, if we've got a series of individual plates that are stood up on the side, we've got a much, much greater heat transfer surface area. It actually occupies a smaller space, but the effective heat in transfer surface area is far, far greater. So we've got a high A value. And if we've got a larger heat transfer surface area, we're less susceptible to fouling. So we've got a very, very high U value. And that in turn means that we can play around with that thermodynamic equation. And it means that we can use the steam at a much, much lower pressure and temperature in order to heat the process up. And as we know, lower pressure steam got more energy contained within it. So it means that we get a more accurate, a more rapid, and a more efficient temperature control of the process, all on a smaller heat exchanger skid, smaller plant rooms. And because of that, it means that we can heat the process up instantly. We don't have to have a buffer vessel of hot water in storage. So different industrial applications have got a preference from moving away from those more clumsy, cumbersome methods of heat exchange that take the energy on very, very slowly. And we need to hold that hot water in storage. And wherever possible, it's not possible for every application, but wherever possible, the vast majority of industrial applications and building service applications are going to want to move towards one of those packaged skids that can generate hot water from steam instantaneously. And there are generally three different reasons and purposes for that. First of all, health and safety. Well, if we think about, I'm going to think about a hospital, or it could be a university. If we're generating hot water for domestic purposes, for showers and hand washing, then of course we need to do everything we can to greatly reduce, or better still, eliminate that risk of legionella. If we've got hot water that's held in storage, then we've got a significant legionella risk. And the recent approved code of practice, it specifically calls out the base of those hot water storage calorifiers as being the single biggest risk to legionella in a process. So if we can move away from a storage heat exchanger to a heat exchanger that generates hot water from steam instantaneously, then we've greatly reduced. I'm not going to stick my neck on the line and say eliminated. I'm going to say we've greatly reduced that risk of legionella. We also know that the temperature profile means that it's very, very difficult to maintain the appropriate temperature whenever we're holding hot water in storage. We may need to put a blast of steam into that heat exchanger when hot water wouldn't otherwise be required, simply to pasteurize the heat exchanger and prevent that risk of legionella manifesting itself. But of course, we know that when we're using that steam, it's going to add to the overall inefficiency of the system. If we've got a client that is very, very risk averse to legionella, could be in a hospital, for example, then it's possible to have flow and temperature sensors on that plate heat exchanger, so we can guarantee that water is moving at the appropriate temperature at all times. And again, we can guarantee that I'm going to use the phrase again, greatly reduced that risk of legionella manifesting itself. Health and safety again. If we're holding hot water in storage, then that vessel, it falls under the Pressure Equipment Directive. Yeah, the thermal energy that's in storage, and that's because of that high pressure to volume product. Whereas if we don't have any hot water in storage, that heat exchanger is not classified as a pressurized vessel. In other words, that plate heat exchanger, it doesn't require a periodic insurance or PED inspection, for the simple reason that, well, If we had an overpressurization or a safety issue on a calorifier, it would go pop. The thermal energy would cause, what we insurance inspectors deem to be a catastrophic incident. If we got an overpressurization of a plate heat exchanger, because those plates are gasketed, and because we're using the steam at a much, much lower pressure, we just have a few wisps of steam that are weeping away from the sides of the gaskets as they relieve it themselves. So if we put a metal shroud around the side of the heat exchanger, that escaping steam is going to condense very, very quickly, safely, and we just have a puddle of condensate underneath the heat exchanger. We're still getting heat exchange, but we've got a visual indication that those gaskets need a little bit of attention. Building service applications, whenever we're using steam to heat hot water up, we need what we call a high limit protection device. It is essentially a secondary valve that sits ahead of the primary control valve. So I've spoken about the risks of erosion in previous presentations. If we've got a poor quality or a poor condition of steam, the risk is that that control valve, it could start to erode and fail. And it's a problem for three reasons. If we've got steam that is passing across that control valve onto the process, there's an inefficiency. We're wasting steam needlessly. There's a product quality issue, especially in food and beverage, pharmaceutical applications, if we don't have an accurate temperature control. But if you think about building service applications, if we've got too much steam going onto the secondary side of a heat exchanger when it's not required, the risk is we could have a dangerously high temperature that could result in scalding. So that high limit valve that sits ahead of the control valve, that is going to register an escalating temperature and it's going to slam shut. It's going to lock off the movement of steam onto the control valve to protect the system. Now, with those traditional shell and tube heat exchangers, the high limit valve needs to be engineered as an entirely separate issue. And quite often, engineers, maintenance teams, over time, they may fail to maintain that high limit valve, or it may be removed. The problem is we've then got a steam system that's at risk of operating unsafely. And if we've got a client that is looking to engineer or replace one of those older systems with a modern, efficient plate heat exchanger on a skid, those high limit protection devices are close coupled to the control valve itself. So it makes it, I'm not going to say impossible, but it makes it very, very difficult to overlook the maintenance and the installation of that all important high limit valve. That makes it easier to guarantee that we've got a steam system that is health and safety compliant. If we're in a hospital environment, the high limit protection that's written into the HTMs as standard. And then finally, on the topic of health and safety, you can see at the image at the top of the screen, the buffer vessel itself is quite large and cumbersome. It could be vertical, it could be horizontal. If it's a vertical vessel, it's going to need laying down so we can remove that tube bundle assembler. That may be a two-man job. We're going to require lifting, training, risk assessments. It could be quite a lengthy process. We had a client 5 or 6 years ago now, whereby when that tube bundle assembly was reassembled, one of the junior staff members, he got one of his fingers caught between the flanges. It had to be removed, unfortunately. So that was a significant health and safety issue, a reportable event. And the only way the client could guarantee that they'd eliminated that risk from happening again was by moving from hot water storage calorifier to a plate heat exchanger. It wasn't the efficiency or the maintenance benefits that were driving that particular project. It was actually the health and safety benefits. But of course, we've got efficiency to think about as well. It could be process efficiency in industrial applications, the speed at which we can heat a process up. Now, it stands to reason that if there's a very, very high energy density with steam, and if we've got a high U value, and if there's more useful heat energy in steam at a lower pressure, and we can increase the A value, the heat transfer surface area, then it means that in many cases we can heat a process up more rapidly and efficiently. Quite often, I'm trying to think of an example. A hospital, for example, if a hospital was moving away from a storage system whereby they've got thousands and thousands of hot water in storage, quite often, years ago, they used to get a little bit nervous that if they got a sudden demand for hot water, there was a concern that it might not be readily available. And the best way I can probably explain how that isn't an issue is if you can think about a hot water distribution network around a hospital, the water that exists within the pipework is likely to be significantly greater than the hot water that's in the heat exchanger itself. So as long as we've sized that heat exchanger to be able to respond very, very quickly towards those that spike in demand, we're simply not going to have that issue. Years gone by, we used to have immersion heaters at home that elevated the temperature of the water very, very slowly whenever there was a demand. And then when we moved from immersion heaters to those instantaneous combi boilers, we didn't have that hot water in storage anymore. But because that demand was met, we very, very rarely have that concern these days. And the thing to bear in mind is I mentioned that those heat exchangers, those plate packs themselves, they're gasketed. So if the process were to change over the years, either increased or decreased, we can manipulate the duty of the heat exchanger simply by changing the overall heat transfer surface area by adding and removing plates. And then from efficiency purposes, well, it stands to reason that if we're only producing the amount of hot water that's required and no more, we're not in danger of the overproduction of hot water. We don't have to consume more steam to pasteurize the coil for legionella purposes. And if we've got a greatly reduced buffer vessel, then we're not radiating as much heat energy out into the plant room. So we can calculate the sustainability benefits by moving from a storage system to an instantaneous system very, very quickly and easily. So those heat exchangers, the plate heat exchangers, are used in a lot of different process applications, as I mentioned. How do we size them? Again, I'm using the example of a hospital application here, just for a point of reference. In a domestic hot water situation, we need to think about the various draw-off points. And once we know what the draw-off points are likely to be, we can calculate the loading units, or the rate at which that hot water is likely to be consumed in litres per second. Now, of course, that applies when we're looking at a completely brand new process. In the vast majority of applications, our client they'll be upgrading a plant room. So they'll be removing an elderly, inefficient hot water calorifier, and they'll likely be replacing it with a more modern, efficient plate heat exchanger. Now, when that does happen, the very, very worst thing we can do is replicate the sizing, the duty of the calorifier, because all we'll be doing is replicating that inefficiency. But like I say, if that were to happen, if we did replicate that inefficiency, it's not the end of the world, because we could simply add or remove those plates in order to resize the plate heat exchanger correctly. Not something we can do with a fixed vessel like a hot water storage calorifier. So controlling the steam, we need to think about the various parameters that heat exchanger is going to be exposed to and how it needs to react. That's going to point us in one direction or another with regards to whether we require very, very basic spring acting controls or whether we need a more sophisticated temperature control valve, electrically or pneumatically actuated. So if our client wanted to retain one of those hot water storage calorifiers, it may be that is more applicable and more suitable to the application, because the heat exchanger takes the energy from the steam on to heat the process up very slowly and gradually. Then a self-acting control is probably suitable for that application. But if we've got a heat exchanger, if we've got a process that needs to respond very, very rapidly and accurately and efficiently, then we are likely to need to move away from a self-acting control towards one of those more sophisticated electrically or pneumatically actuated controls. So again, with a steam heat exchanger, it's vitally important that not only do we bring the steam onto the heat exchanger at the appropriate mass, pressure, temperature, energy content, but we get that condensate away at the appropriate rate. And I've kind of contradicted myself a little bit here, because I mentioned that steam's got more energy contained within it at a lower pressure. But we want to make sure that that pressure is not too low. Otherwise, we're not going to have sufficient motive energy to push the condensate out of the heat exchanger itself. So we need to think not only how we're controlling the steam coming onto the heat exchanger, but how we're getting the condensate away from it. Other things to think about, those individual plates. It's not just the number of plates that we have, but it's the pitch, it's the angle of the pitch of the plate. The checker part of the plate, the chevron in the middle, that's where the steam heat exchange actually takes place. So if we've got a high theta plate, which has got a very, very shallow pitch, it essentially means that we're promoting more turbulent flow moving across that plate. So turbulent flow means that we get more heat exchange, if you like. The downside of that is we've got a greater pressure drop. And the opposite's the case if we've got what we call a low theta. It means that we get less heat transfer, but we get a lower pressure drop. The question really is the impact of the duty of the pumps that are required on the secondary side. So if we've got a client that's replacing a shell and tube calorifier with a plate pack, if they want to keep the original pump set on the secondary side, one of the first questions is, what pressure drop are we aiming for? And again, that'll help us to size the appropriate number of plates and to determine what the chevron pitch needs to be. Again, it's not the end of the world, because if for any reason that was engineered incorrectly, it'd just be a case of adding or removing the appropriate number of plates to play tunes with that pressure drop requirement. Something we can do when we've got a gasketed plate pack, something we can't do when we've got a fixed surface area like a shell and tube heat exchanger. Air venting is also critically important for reasons we've gone through. Keeping the steam dry, as we've mentioned, the drier the steam, the more energy there is present within the steam. So it really brings home the importance of correct steam generation and steam distribution to ensure that not only are we removing the moisture from the steam before we use it, but we're getting the air away as well. Control valves. We've mentioned in that previous presentation that control valves, they need to be sized in accordance with the mass of steam that is being moved. Never want to see a control valve sized on line size. If it is, chances are it's going to be oversized. An oversized control valve operating very, very close to its seats, of course, is more susceptible to erosion. When we get erosion, we've got a high cost of maintenance. We've got an inaccurate control of temperature at the process. And we're going to find that those high limit valves are more likely to be tripping out on a regular basis. So this really demonstrates how we go back to one of those thermodynamic equations. If we know the mass of steam that's required, then if we know the Q value, then we can rearrange that equation in order to determine the mass flow rate requirement that control valve needs to distribute onto the plate pack. Now, if you remember that rule of thumb we spoke about, that 1.8, if we multiply that 300 kilowatt by 1.8, the answer is 540 or 540 kilograms per hour. So it really demonstrates the value of remembering that 1.8 rule of thumb. Doesn't replace those thermodynamic equations. I'm very fortunate on this occasion that the figures bear me out. But again, it demonstrates that we don't want to be sizing that control valve on line size. So those steam traps, we spoke about them last week. They're vitally important, especially that they need to be sized and selected correctly. Because if we're not getting that condensate away at the appropriate rate, it is going to back up and flood the plate pack itself. So there's a lot of information to go through. I appreciate I've gone through it at a very fast pace, but hopefully I've given you a few insights and a few interesting pointers there that we need to take on board or take into consideration whenever we're using steam for heat transfer purposes. Steam is a fantastic source of energy. We've just got to apply best practice in how we generate, distribute, and control the steam in order to achieve that. So that brings to an end the fourth presentation in the series. Next week, we're going to look at how we need to remove, manage, recover, and reuse the condensate that is the byproduct of heat exchange. But I'd also just like to remind you about that page. Any of you that are graduates that are interested in looking at our Year in Industry program or getting further information with regards to any postgraduate opportunities, please do take a little snap of that QR. Again, just to remind you that I will make a PDF of the slide deck and an attendance certificate available if that is likely to be of interest. All I ask is that you drop me a message on LinkedIn. Please do interact with myself and Brian on LinkedIn as well. You know, please do join our network, follow us. If you've enjoyed this series of presentations, you know, please do put a comment on there. Any feedback could be very, very gratefully received. But on that point, I'd like to thank you for your attendance this evening. I'd like to hand back to Brian and see if there have been or if there are likely to be any questions. Thank you.
Okay, thanks, Dan. As usual, top notch. So enjoyed the presentation again. Plate heat exchangers, been involved with them over the years. Although I did just miss here because I didn't have my headset on when you said erratic and you were talking about plate heat exchange. I thought it said erotic, and I thought I've never come across those before. And also the point about health and safety, absolutely critical, which whichever aspect of engineering you're involved with, there's always risks involved, so please be careful, everybody. And the sustainable benefits of the plate heat exchangers, the obvious when you just look at them, the size of them, they're really neat. And getting back to the old subject of air venting and dry steam came in at the end, so that's brilliant. So really enjoyed it again, Dan. So there's no questions come into the chat that I can see, which is fine. So on that note, we've just got a couple of minutes left. So thank you again, Dan, and the guys at Spirax, Sarco. It's lovely that you take the time out to present this information to the engineering community. Thanks to the Western Area IMechE committee. If anybody's interested in being a volunteer that's part of the IMechE, either contact myself, or if you go to the IMechE website, you'll be able to just follow you have to do a few clicks to get to the Western Area IMechE committee page, but you'll be able to make contact that way. Thanks also to the University of Huddersfield. Hopefully we've got some students online. If you enjoyed this evening, spread the word, spread the love. It's an interesting subject, and when you get out into industry, trust me, you will get you will be involved with it without a shadow of a doubt. And thanks to Projex Solutions for supporting this. And just a reminder that the next lecture. Hello. Oh, sorry. Hello. We've got a reminder that the next lecture will be on condensate management, and that'll be on Wednesday the 16th. So just to throw a curveball in there, so it's not the usual Tuesday night, it's Wednesday the 16th. So it's thank you. If there's no more no questions coming through, thank you, and a good night from Projex Solutions. And cheers, Dan. Talk to you soon.
No problem. Thank you. Good evening.